Okay, we are still proving the Picard-Lindelöf theorem. So now we have changed it. We have shown that the general initial condition can be transformed to the initial condition at the origin. And we have also shown that the differential equation with the initial condition at the origin is equivalent to this integral equation, right? So the next step is to show the existence of a solution of this integral equation. Well, existence and uniqueness, but uniqueness is homework. So existence is going to be proven through a series of exercises. Okay, now the next step to do it, to prove that this integral equation has a solution, is actually quite a clever trick too, but this trick is quite common in mathematics, so it's not something too original. I'm not sure, maybe Picard and Lindelöf, they were the first ones to invent this trick, and then it spread into other areas of real analysis. I don't know, but this is kind of familiar. So, and the trick is very beautiful too. Now the idea is that we don't know what y is, right? So we're going to try different values, different functions as candidates for y. So we are going to first try the function phi 0, which is just 0, as y. So what do I mean by this? So we're going to substitute this instead of y into the right hand side and see what we get. So when we substitute this into the right hand side, then we get f of s and 0 ds. Then we integrated this is some expression in terms of s. Then we integrate it from 0 to t. Then we get some expression in t. And then, well, of course, it's not going to be 0. Otherwise, it will be too good. So this is going to be some phi 1 of t. But then we're going to continue. So phi 2 of t is going to be the integral from 0 to t, f of s and phi 1 of t ds, and so on. And then you guess where it goes to. So phi n plus 1 of t equals the integral from 0 to t f of s phi n of s ds. Now, so what is good about it? So the good thing about it is that now we can take the limit. So suppose that the limit of phi n of t as n goes to infinity, for every specific value of t, you can just take the limit as n goes to infinity, and then suppose that you are going to get some expression in t, and then we're going to denote it by phi 0 of t. Right? Then, what happens if we take this definition and we take the limit as n goes to infinity? So if we take the limit as n goes to infinity, sorry, not phi 0, it's just phi 1. Phi 0 is 0. Sorry about that. So then phi n of s approaches phi of s. So I'm going to just replace it with phi of s. Phi n plus 1 of t. But phi n plus 1 of t is the same sequence as the original one, only it is shifted by one element. Alright, so if this is the sequence, phi 0, phi 1, phi 2, phi 3, and so on, then this is phi 1, phi 2, phi 3, and so on. But of course the limit is the same. It's just like, I don't know, the limit of, say, 1 over n plus 1 is the same as the limit of 1 over n when n approaches infinity. Because these are essentially the same sequence. Only this one looks like 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. And this one is the same thing, only shifted 1/2, 1/3, 1/4, 1/5. But the limit is, of course, the same. So the limit of this is also phi of t, which means that the limit of the sequence is going to be the solution to our integral equation, right? So what is what is more to prove then? So there are two main things. So one thing is to prove that the limit exists, and another thing is to prove that this operation, taking the limit of an integral equation, is actually a valid mathematical operation. Now, the latter part, showing that taking the limit is a valid mathematical operation, I think you'll just have to take my words that you have to show that the sequence phi n of t converges not just pointwise but uniformly. And you have not learned the notion of uniform convergence from real analysis yet, but you have to believe me that the three steps, the three exercises that you went through in class and in homework, they not only show that this limit is phi of t for every specific value of t, but also that this is the sequence converges uniformly, and therefore this operation of taking the limit in the integral equation is actually a valid operation, right? So this is the part that we're going to skip because we lack the knowledge from real analysis. But the part about showing that the limit exists, showing that the limit of phi n of t actually is something, is a well-defined function of t. This is what you can do, and you have done part of it in class, and you are going to do part of it at home. So at home is actually the easy part, so not much is left after class. But anyway, let me maybe, just to give you more intuition about how this works, let me go through a specific example of calculation of this phi. So this is called the method of successive approximations, and let me write it here. So phi n plus 1 of t is the integral from 0 to t f of s phi n of s ds. And here is an example. So here dy dt equals t squared minus y, the same equation as before. So y of 0 is 0. So now this right hand side is our f of ty. So how do we calculate our phi 0, phi 1, phi 2, and so on? So phi 0 is always 0. Phi 1 is going to be the integral from 0 to t of this thing. But in this thing, instead of t, I need to substitute s because I'm going to integrate with respect to ds. So s squared minus, and y is going to be previous phi. In this case, phi 0, which is 0. So 0 ds. Right? And the antiderivative of s squared is s cubed over 3. So this is t cubed over 3. Now, phi 2. So phi 2 is going to be the integral from 0 to t. Then t squared becomes s squared minus a y. Instead of y, I need to substitute the previous phi, which is t cubed over 3, but I need to replace t with s. So I'm going to write s cubed over 3 ds. And this is, now note that this s squared is still present, and it's going to give us t cubed over 3. So this is going to be t cubed over 3. And here I have this s cubed over 3, so it's going to be minus t to the 4 over, I will write 3 times 4, you will see why in a minute. So now phi 3 is going to be the integral from 0 to t square, which becomes s square. So s square is still here, which means that when we integrate, we're still going to have this t square, so minus. Now, the previous y is this. Only I need to replace t with s. So I'm going to have s cubed over 3 minus minus plus s to the 4 over 3 times 4 ds. And now I can integrate. Integrating s square from 0 to t, I'm going to get t cubed over 3 minus. This term is exactly same as here, so I'm going to get the same t to the 4 over 3 times 4 plus, and that's a similar term, so I'm going to get t to the 5 over 3 times 4 times 5 now. And so on. Now, when we continue this sequence, so now that in every step we just add one term here, so which means that eventually the limit as n approaches infinity of our phi n of t is going to be just the infinite sum of all these terms. So I'm going to write the infinite sum. I mean, so there's going to be the next one is minus t to the 6 over 3 times 4 times 5 times 6 plus t to the 7 over, and so on and so forth. Now, what is here? How do I simplify it? So note that I can multiply and divide by 2. So I'm going to write 2 times t cubed over 2 times 3 minus 2 times t to the 4 over 2 times 3 times 4 plus 2 times t to the 5 over 2 times 3 times 4 times 5, and so on. Right? So what else do we have? Then I can just multiply by 1. It doesn't change anything. And then in the denominators, I will have factorials. Right? So this is going to be the sum of the following terms. So I'm going to have 2 to the n over n factorial. Then the sum begins with the third term. So 3 to infinity. Yeah, and then I'm going to have alternating plus and minus signs. Right? To make alternating plus and minus signs, I need to multiply by minus 1 to the n. However, if it is just minus 1 to the n, then they are alternating, but when n equals 3, I get minus 1 cubed, which is minus 1, and I should have plus 1, because the first term is positive. So I'm going to have to write plus 1. So now they're still alternating, but at least they begin with the plus sign. All right? So by doing these successive approximations, I have constructed the limit phi n of t in the following form. And then if you think about it further, you will see that this is nothing else but the Maclaurin series for the answer. So this is actually the Maclaurin series is Taylor series at 0 for the function. What was the function? It's 2. Yeah. Let me check my notes. T square minus 2t minus 2t plus 2 minus 2 minus t. So this is just the Maclaurin series for this function, which you can, I hope you know how to compute the Maclaurin series, or you can just enter it in Wolfram alpha. You will see that that's exactly it. All right, then I'm going to give you one more example of this. The reason is because this was actually a linear differential equation, and if we try to do the method of successive approximation for a linear differential equation, then it's always going to come out nicely, and the limit is going to be the Maclaurin series of the solution. Well, but it's not always like that. Just to show you that, generally speaking, it could be much more complicated. Let me give you another example. Let's say y prime is going to be equal. Yeah, I've prepared it here because it's a bit complicated. So let me take my notes. Is y minus 1 squared. So y of 0 is 0. Now, phi 0 is still 0. Phi 1 of t is the integral from 0 to t of this, where instead of y, we are going to write the previous phi. So 0 minus 1 squared ds. Now, now it's simple because this is just 0 minus 1 squared is 1. Integral from 0 to 1 is just t. But look at phi 2. So phi 2 of t is going to be the integral from 0 to t of this, where instead of y, we should write this previous function, and now it should be a function of s. So it should be s minus 1 square ds. Now the antiderivative is s minus 1 cube over 3. From 0 to t, I'm going to get t minus 1 cube over 3 minus, when s is 0, I'm going to have minus 1, so it's plus 1/3. And this is t cubed minus 3t squared plus 3t minus 1 plus 1 over 3. Now minus 1 plus 1 cancels out, 3 over 3. So I'm going to get t cubed over 3 minus t squared plus t. Well, I'm going to give you one more term, just so that you have some idea how complicated they become from 0 to t. Now I need to use this as y, and I need to change t to s because I'm integrating with respect to s. So it's going to be s cubed over 3 minus s squared plus s minus 1 squared ds. Now note that this is a cubic function, so degrees 3, squared degrees 6, integrated degree becomes 7. And this is already a very complicated integral. I didn't do it myself, of course, I did it in Wolfram alpha. And the answer is that this is t over 63 times t to the 6 minus 7 t to the 5 plus 21 t to the 4 minus 42 t cubed plus 63 t squared minus 63 t plus 63. Well, and then you imagine that if you try to take the next term is going to be, this is a polynomial of degree 7. So when you take it minus 1, it's still degree 7, squared degree becomes 14, and then integrate degree becomes 15, and so on. So every next polynomial has twice as high degree, or twice plus 1 as high degree as the previous one. So the number of terms very quickly grows, and the terms are not even repeated exactly, because, well, if you look at this polynomial, and let's look at the terms here for this polynomial. T, well, there is T over 63 plus 63, so T is here. Minus 63T times T over 63, so this is minus T squared. How about T cube? And note that the term at T cube, it has the coefficient 1, so T over 63 times 63T squared is T cube, and here the coefficient is 1/3. So which means that they're not just repeated. These two are repeated, but the next one is not repeated. It is being transformed. So of course, I guess it is possible to figure out the general pattern and to see that how exactly to express the final answer in the form of a power series, but it's more complicated here, right? So which means that when you need to prove a general theorem that the limit of phi n always exists, it's maybe kind of tricky. It is not too tricky as it happens, because you've done it, you've done part of it in class, and there is a small part at home, but that was just an explanation of why this is a challenge.